Welcome everyone. My name is Heather Gray. This is Data 670 with Professor Dr. Jon McKeeby. I'm in Group 2 and this is presentation 3. I'm predicting exciting projects in donor churn at donorschoose.org. All right, in a quick overview, I'm just going to review what donorschoose.org quickly along with the project scope, data and analytics approach, and then I'll go over the model descriptions, accuracy measures, results, model comparisons, recommendations for future research, lessons learned, and references. Okay, and how DonorsChoose works. What happens is teachers post a project online, something they think they'll improve the education of their students. Donors log in, they select a project, and they can donate as little as $1 towards purchasing the items that the teachers need. And then once it's fully funded, DonorsChoose purchases the items and mails them to the school. Okay, and for the project scope, the objectives are to create 2 reliable predictive models that can be trusted to work on new incoming data at DonorsChoose in order to increase funding. Currently, they have over 37,000 project requests, which makes it really difficult for donors to search through and select the ones they like. And what's happening is quality projects expire after very few views, and ultimately fewer students are being reached. And it just results in slow and low funding. Okay, and on the is exciting projects, model 1 is to predict exciting projects. The binary target is exciting. 1 is equal true. It was rated is exciting, and 0 is equal to false. Predict which models are exciting so that they can be referred earlier. Submissions are considered exciting if they have qualities beyond what is typical. And those qualities that DonorsChoose, they decided were these following criteria. So the project has to meet these. It is fully funded, which is not used in my modeling because I wanted to predict exciting before the project was fully funded. At least one of the donors was referred by a teacher. It has a higher than average percentage of messages left by donors. At least one donor that paid with PayPal, Amazon, credit card, or check has one or more of the following: 3 or more donors not referred by teacher, 1 donation of $100 or more not given by a teacher-referred donor, and a donation from a thoughtful donor. And I just have here this graph on the side here to show you most of the projects are fully funded, but most of you can see the tiny little bit that are rated as exciting. The bottom part of the graph, and this is raw data, so there's some missing data, but in the sample that SAS used to generate this chart, you can barely see like a little bit of the is exciting projects. I think in the entire sample it's 7%, and the sample I used for this, the is exciting projects were around 10%. All right, and for churn, this is model 2. Predict which donors are most likely churn. Binary target where true is equal to 1, which is they do churn, and false is equal to 0, which would mean they're a repeat donor. Approximately 34% of the donors in the sample churn. The average donor retention rate in 2016 was 45%. So it means that in this particular sample that I used, that donors chooses a little bit ahead of the game. Repeat donors are an effective way to increase funding, which is why we're trying to predict churn so that offerings can be made by DonorsChoose ahead of time to encourage them to come back with doing things like offering discounts with corporate partners and donation matching. All right, and just a quick review of the data set. These are projects submitted to DonorsChoose from September 2002 through December 2013. The data supplied contains almost 7 million rows. It was 79 variables, of which 18 are numeric and 61 are nominal. It's a 50,000, the sample I took from this ended up being 50,000 rows, and they supplied the information, the data in 5 files, and they were in relational database format, where project ID is the primary key. You can see it's an essay file, projects, resource, outcomes, and donations files. For data prep, the sample was reduced to 50,000 rows. It was a random sample. The variable selection ended up leaving 29 variables selected using the Guinea index in SAS Enterprise Minor, and also by removing highly correlated variables. Imputation was performed. Enterprise Minor does this for interval variables by imputing based on the variable's distribution. And for categorical, I set it to impute using the median. For binning, I also performed binning. This helps to deal with outliers and skewness. And you can see in those 2 graphs below there the result of bidding on a non-teacher referred count. For transformations, this is to handle SKU distributions. I only had 3 continuous variables left after variable selection, and they all ended up being log base 10 transformations. And you can see what log base 10 is, as if there's a right tail, it brings that tail in and brings the distribution in a little bit. And you can see by how the scale has changed on the bottom of those graphs. And then the data is partitioned before modeling into 40% training, 30% validation, and 30% test data. All right, in the analytic approach, the tools I use were SAS Enterprise Miner, R, and SAS Jump for some of the graphics. I use the SAS SEMA approach, which is just the logical way to use SAS Enterprise Miner. And it's sample, explore, modify, model, assess, and that's just to cut out a picture of what my flowchart looks like. The data is retrieved and reduced to a size that is appropriate for modeling. In the exploration step, we explore the data to learn its characteristics. This includes reviewing basic statistical summaries, variable graphs, missing values, and outliers, etc. Then we go to the modification step, which is data prep according to the findings in the exploration step and according to what's required for the specific modeling methods that you're using. Then the models are run, and then we select the ones that perform the best. And for assessing performance on these 2 target variables is exciting. I was looking for high sensitivity rates, and for churn, I just wanted a really low altogether low misclassification rate. All right, and for logistic regression, binary targets, so we have supervised learning models for classification. The logistic regression method for binary classification creates a linear model out of the nonlinear relationships between the dependent and independent variables by using the log of the odds ratio. I chose this one for this data because it's a simple model that could allow for decision makers at donors choose to see the relationships between the variables, and it allows them to make inferences. Here's an example. Does the probability of donor churn change with an increase in non-teacher referred count? The selection method was forward selection. It's a stratified sample because I needed an oversampling method because it's exciting, it has rare cases. And then for churn, it was just simple random sampling. The cost function that I talked about in previous presentations, it didn't improve either model, so you might see some of the results in some of my pictures from SAS Enterprise Miner, but I don't really discuss it for that reason. All right, and the neural network. Neural network is a method that learns from large amounts of training data. It will build a set of rules from the training data so that it can automatically make inferences on new and coming data at donors choose. And this is a really simplistic picture of how it works. You have the input layer. This is where the data comes in. Independent variables are fed in and weighted by their importance before being passed to hidden layers. The hidden layers, they filter the redundant data and pass the filtered data to the output layer. The data is weighted by its importance also before being passed to the output layer. In the output layer, it takes the data from the hidden layers, converts it to a value between 0 and 1. The closer the value is to 1, the more likely the project is rated as exciting, or the most likely the donor will churn. And the red arrows, you can see I have it there in gray, they represent the what's called an activation function, which I will get to in just a moment. All right, model description. This is the neural network continued. This was chosen for donors choose because it works well with highly variable data, and it finds relationships whether between variables, whether linear or nonlinear. And let's see, for the parameters I used in SAS Enterprise Miner, for is exciting, the activation function was a radial basis. There's 2 hidden layers for that model. And in churn, the activation function is linear, and there's 3 hidden layers. All of the other parameters were left at their default values. All right, for support vector machine, a support vector machine is a supervised learning model that seeks to separate the classes of the target variable by finding the maximal marginal hyperplane in n-dimensional space between them. This was chosen for, I picked this for donors choose because it can also model linear and nonlinear data. It's effective when there's a high number of variables. It's not affected by outliers, and it only uses support vectors as the decision function, so it takes up less memory. The downside is that when the data set's large, support vector machines can be computationally expensive. Parameter setting for that model in SAS, I ended up with a radial basis function, a cost parameter of 1, and a radial basis function for churn also with a cost parameter of 1. All right, and the accuracy measures that I chose for these models for is exciting. Sensitivity rates are important because we want to get at those rare cases. So I use that. And for churn, overall classification accuracy is important. For logistic regression models, I use ROC curves, misclassification rates, and confusion matrices. And for the neural net and support vector machine, I use the cumulative lift charts, misclassification rates, and confusion matrices. Okay, and here's my results for the is exciting target. The cost function didn't approve it. I've already mentioned this, so it's left out of the discussion. The is exciting ROC results in the figure below show that both models performed extremely well, as they both intersect very close to the 100% classification mark, which is in this top left corner. And they almost all overlap completely, so I got really good results, overall classification rates from this model. All right, and further results for is exciting. Here's the misclassification rates. You can see that the model is a little bit overfit because the misclassification rates increase as it goes through the validation and misclassification sets. And in the is exciting confusion matrix, you can see the rates are low, but they still result in a lot of the positive cases being missed. Because the sensitivity rate, which is key, is 87.23%, and the specificity rate is 99.8%. And we would rather have a 99.8% sensitivity rate. All right, neural network results for is exciting. It's radial basis function with 2 layers. You can see the red lines at the bottom of the screen at the number 1. This is where the lift curve would be if there were no model at all, which, for example, it's random guessing. The cumulative lift charts for the training and validation set show how well the model performs versus having no model at all. The blue and green lines in both sets are very similar, which tells us that the neural network performed well. Right, and neural network results continued. We can see the increase in misclassification rates that the model is a little bit overfit. We can also see that the overall misclassification rates are extremely low. But again, when we look at the confusion matrix, let's see, the sensitivity has improved from the logistic regression to 92.5% on the validation data. So that it is a little bit of improvement over the logistic regression model. All right, in support vector machine results, here's the cumulative lift chart. It was a radial basis kernel. The cumulative lift line is very close to the best possible cumulative lift line, and they performed similarly to the neural network, which both of them performed extremely well. All right, and overall the model is relatively well fit. You can see our misclassification rates there. It goes from, they stay close to around 1% misclassification. And you can see the number of wrong classifications there in that bottom row compared to how many total cases there were. And that's overall. That's like true positives and true negatives. The confusion matrix shows that the model is finding all of the true negatives, but the sensitivity is 90.4% for the validation set. For this model in the neural network, I think the question that would have to be raised is this number of missed cases reasonable? You see that missing 37 cases on the test set, that's a lot of cases overlooked by the model. So I guess whoever the decision makers would have to decide on the neural network and the support vector machine is if that's reasonable, if we need to improve the model or use a different model. All right, and logistic regression model for churn, I'll just give you a heads up. For the churn variable, none of my models worked out well, so I'll just review the results quickly. Let's see the ROC results here. You can see they performed poorly. The green line would be as if there were no model, so you can see how close the red lines are to that. Yeah, I think the most that can be said, it's a little bit better than taking a random guess, but that's about all that can be said for this model. All right, and here's the misclassification rates for churn in the logistic regression model. It's just further evidence that the model isn't identifying relationships in the data to predict churn accurately. And from the confusion matrix, you can see that the sensitivity rate is 44% on the validation data and specificity is 28%. All right, and let's see from the cumulative lift chart below, we can see that this method did not perform well either. You can see the model line in both. It's the neural network line, the blue line, is halfway between the red line and the green line in the top chart, and then it gets closer to the red line in the bottom chart. So this one didn't perform well at all. And you can see it's really overfit too, because it does well in the training data, well, does better on the training data, not well, and then it really starts to fall apart on the validation data. Okay, and then just here's a view of the misclassification rates. It's all between 20 and 30% misclassification. The sensitivity rate was 46% and specificity is 76%. So more proof of how bad these models did not work out. All right, and support vector machine, radial basis kernel, very poor performance on the validations data. And this is another really good example of a highly overfit model. You can see it actually looks good on the training data, and then it completely falls apart on the validation set in that lower, you can see in that lower chart. All right, and more poor results from the churn support vector machine. Here again, the misclassification rates are even higher. As you can see from those rates, 37 or 3.7 on the training, but then it goes to around 30% for the validation and test. The sensitivity rate is a whopping 1.4% and 65% for the validation set. So although it's highly overfit, for some reason it did do a better job at finding true positives, but this model still couldn't be used for this data. All right, here's the Is Exciting model comparison. SAS Enterprise Minor chose the neural network because of the overall misclassification rate on the training data. You can see there in the chart. See, it was for misclassification rate on the training data ended up being less than 1%. And then the sensitivity rate, which was so important for this particular target, the neural network also did better in that aspect also. So if we had to pick between any of the models, I would choose the neural network. And for churn, these results are so bad I don't even want to talk about it anymore. The no lift model is that bright orange line at the bottom, and so you can see where the other three models performed. The green line is the support vector machine, the red line is the neural network, and the blue line is the logistic regression. So the support vector did better, but it's still not a good rate. And then more misclassification rates of just everything's between 20 and 30% of misclassification overall. Okay, and recommendations for further research for the Is Exciting model. The model definitely needs to be tested on more recent projects, and also to change the way exciting projects are rated by adding newer, more relevant variables. For instance, the Kaggle site indicates that teachers who donate to exciting projects have a higher probability of creating one, so a variable that reflected that relationship would be helpful. And also, since this data set was issued, Donors Choose is added new options to the site. For example, they let you know if a project has a 2x sponsor, and this is a sponsor that will match the donations that are coming in for that project. So a variable that reflected that would also be helpful. Look for ways to improve the sensitivity rate on the neural network, maybe by adjusting parameters, and try other types of neural networks. For instance, a recurrent neural network works on the principle of saving the output of a layer and feeding this back to the input to help in predicting the outcome of the layer. And then there's also modular neural networks. And these are collections of different networks, and they all contribute to the output. Okay, and recommendations for further research for churn. I think feature engineering would be helpful, because with the exception of the churn variable, only 3 other variables that remained after variable selection were directly related to the donor. And here's just a couple examples. We could add in maybe average donation, the number of times donated to each poverty level, a number of times a donor donated to each grade level. I think certainly maybe find more appropriate modeling methods, and maybe even try different modeling environments, because this one is limited to SAS Enterprise Minor. All right, and lessons learned from Data 670. I learned lots of them, but here's just a few. I've learned a lot more about predicting these particular predictive modeling algorithms, support vector machine neural network and logistic regression. I have used them before, and I knew how they worked before, but I learned a lot more about the parameters that are being adjusted in SAS Enterprise Minor and what adjusting those parameters is actually doing to the model. I learned more about SAS Enterprise Minor. I was introduced to SAS Jump, and of course I learned more about R and R packages. For data prep and transformations, I learned a lot more detailed information about when and why and how to do those. I learned a lot from a book called Applied Predictive Analytics by Dean Abbott. He has a great section on exactly that, when and why and how these transformations should be done, or when they should be done. I learned about stratified sampling or oversampling to get at rare cases, and accuracy measures. The cumulative lift chart, I learned quite a few new accuracy measures. The cumulative lift was my favorite. I think it's because I had such a hard time understanding it before, and I don't know why I did now. But I just learned it's a really helpful chart to use. And of course, from doing these presentations, I've become a lot more comfortable giving them. And I think that wraps it up. Thanks everybody for listening. My references are on the next page if you're interested. Thank you.